So we've seen that when no external forces are acting on a system, then momentum is conserved. But we don't always have the situation where there are no external forces. So what happens if an external force is acting on a body? Well, we've seen this before, but let's look at it again. We know from Newton's second law that the external force is equal to ma, and the acceleration is just dv dt. So this is equal to m dv dt. And then as long as the mass isn't changing for an object, we can write this as d mv dt. And we've seen that the momentum p is just given by mv. So the force is equal to dp dt, which tells us when we have a force acting, then the momentum is changing. So the change in momentum is dp is equal to f dt, just rearranging the equation that we've just derived. So now if we want to work out what the change in momentum is over a longer time period, so remember dp stands for a really small change in momentum and dt stands for a really small change in time. Well, if we want to consider larger changes in momentum and larger changes in time, we're going to need to integrate this expression. So let's assume that at time t1, the momentum is given by p1, and remember momentum is a vector, and at time t2, the momentum is given by p2. Well, in this case, we can put these limits on the integral. So our left-hand side becomes the integral of dp with the limits from p1 to p2, and the right-hand side is the integral of f dt, and we're going from time t1 to time t2. Now, if the force is constant over this time period, this integral is very easy. We can just pull the force out the front, and when we integrate these two, we've got a p on the left-hand side and an ft on the right-hand side, and then we substitute in our limits. So on the left-hand side, we've got p2 minus p1, and on the right-hand side, we've got the force F times t2 minus t1. So P2 minus P1 is just the change in momentum, delta P, and T2 minus T1 is just the change in time, delta T. Now, that was all very easy if F is constant. If the force is actually changing over time, it's not too bad. All we need to do is replace that force, F, in our equation with the average value of the force. So we just end up with F average. So our equation is now the change in momentum, which is delta P, is equal to F average times delta T. Now, this expression actually has a special name. It's called the impulse, and we will be giving it the symbol I. In some textbooks they use the symbol J, but we'll use I. So the impulse is a vector. It's equal to the change in momentum, which is also equal to the average force times the time for which that force is applied. Now, because the impulse is just the change in momentum, it has the same units as change in momentum, so the units are kilogram meters per second or Newton second, whichever one you prefer. So we can calculate this, or sometimes, depending on what we're given, we can read it off a graph. So if we're given a force versus time graph with force on the y-axis and time on the x-axis, then the impulse is just the area under the curve on the force time graph. So let's now have a look at a problem that we can solve using impulse.
So the problem, a ball bounces off a wall. The ball has a mass of 100 grams. It bounces off the wall at the same speed it hits with, 2.0 meters per second. The angle the ball makes with the vertical as it approaches and leaves the wall is 30 degrees as shown. The collision lasts 0.010 seconds. Part A, what is the impulse from the wall on the ball? Part B, what is the average force the wall exerts on the ball? Okay, so to answer part 1, we know that the impulse is equal to the change in momentum, which is equal to the average force times the time. So to answer this question, what we can calculate is the change in momentum, as we've got the initial speed here, and we've got the initial velocity here, and the final velocity here. So we know that the change in momentum is equal to the final momentum minus the initial momentum, which is equal to the mass times the final velocity minus the initial velocity. Now, because all of these are vectors, well, not the mass, the momentum and the change in the momentum and the velocity are all vectors, what we'll want to do is break this into components, and we'll draw little axes here. So this is the x direction and this is the y direction. So if we work out the initial and final velocities in the x and y direction, then we can work this out. So let's let the initial be yellow. So we'll look at this initial velocity here. This is 2 meters per second, and we're splitting it into an x component here and a y component here. So this is Vx, and it's going down. This is Vy, and we'll give it a little subscript I as well to show that this is initial. And if this angle here is 30 degrees, then this angle up here is 30 degrees as well. So what we can write is Vx initial is going to be equal to, because it's opposite this angle, it'll be V, which is 2 times sine of 30, and 2 sine 30 is equal to 1 meter per second to the right, and Vyi is equal to 2 times cos 30, and so that is equal to 1.73 meters per second, and this is down. Okay, now we're also going to need to calculate the final. So to get the final, we break this final velocity, which is again 2 meters per second, into these two components. This angle up here is 30. So Vx final is equal to 2 times sine 30, which is equal to 1 meters per second, still to the right. And Vy final is equal to 2 cos 30, this side, which is 1.73 meters per second up. So delta P is equal to delta Px plus delta Py. And so delta Px, you can see in the x direction it's not changed. So delta Px is equal to Vx final minus Vx initial, which is equal to, well, and then we need to multiply by the mass. But Vx final minus Vx initial, that's just 0. So the change in momentum is 0. And in the y direction, we've got m times Vy final minus Vy initial. And so this is equal to, well, it's 100 grams, so it's 0.100 kilograms times Vy final, which is 1.73, that's up, minus 1.73 down. When we minus a down, then we can add an up. So this is up. And so solving that, we end up with 0.346 up. So our final answer for the impulse is equal to 0.35 kilogram meters per second vertically away from the wall. And then part B, we're asked for what's the average force. The average force is equal to the impulse divided by the time, just from rearranging our equation that the impulse is equal to the average force times the time. So we've just calculated the impulse, it's 0.346, and the time is given up here, it's 0.010. And so solving this, we end up with 35 newtons. And once again, this is away from the wall. So hopefully that gives you some idea of how to solve problems using the impulse equation.